Today we start one important topic, real analysis. Real analysis, one of the major subject of mathematics, and also handles all related topics of mathematics and gives the roots of mathematics. So we start from beginning and we start real analysis with one familiar book. Walter Rudin is the writer of this book, Principle of Mathematical Analysis. We start the portion real and complex number system. Okay, all are understand real number because familiar with in previous class, and but I also till now some from basic. That means we start from rational number. Okay, rational number. Rational number are those number of from m by n where n not equal to 0 and mn belongs to 0. Okay, those number are called rational number. We also known about that which one are rational number. So now we see it, and we also give some example. 1 by 2, 2 by 3, those are 4 by 5, those are rationals. Okay, and we denoted it by q. So next, how we find how we going to further progress, and p square equal to 2 when if p belongs to q. This one possible or not? This is possible. If we find this answer of this question, then we see about that. Just rational number are not belongs. That means some other numbers also belong. That's not form of this way. Okay, that means that is not represented by this way. So we then construct some another number. Those are irrational number. Okay, and these number are approximated by any finite decimal or any rational number. Then we see about that this implies that p equal to root 2, and this root 2 is approximated by 1 and 1.4, 1.414, 1.4142 dot dot dot. Okay, in this way we extend the decimal number place. Then we also give some accurate result, but not exact to root 2. Okay, because any irrational number is not handled by or not exactly approximated by any rational number, but close to rational number. Okay, so in this way we develop some portion, and also we done this p square equal to 2, how this one is not rational belongs, or why this one is not done, why we not write in this way, we discuss about now. Okay, so p square equal to 2, we write we talk about that if p equal to q, then p equal to m by n. Okay, n not equal to 0 and mn belongs to z. Then this implies simply m by n whole square equal to 2. Then this implies that m square by n square equal to m square by n square equal to 2. Okay, this implies that m square equal to 2n square. That means this one is even and this one must be even, because this one even, so m square is even, and we know about that m square is even means m is even. Okay, then m is even, and m is even, we talk about that m equal to 2k in this way, where k belongs to z. Then we put here, then we get 4k square equal to 2n square. This implies that n square equal to 2k square. That means n square is d even, and this implies that n be even. Then m even and n even we write in this way, and we get this two, m even and n even. Okay, then this one in this way. How we not represent in this way? So there is some contradiction, and this contradiction, that means we follows from this contradiction that m by p not equal to m by n. That means p not written by in this form. Okay, so next we going to another portion or another problem. We understand this questions and this problem also. So in this way we develop some rational number from rational one. Okay, first we handle integer number or natural number. That means 1 2 3 4 5 6 7 8 9 0, and then we done some integer number, that means -1 -2 in this way, and next we develop rational number and going to some problem and create some problem and also develop rational number. In this way we develop all real numbers, and obviously then we going to further complex number. Okay, that means some here we write -2, then this one is not represented by any real number, then this one is going to be another way this one is represented. So this type of number is called complex number. Now we're going to further one important topics or important questions. Okay, now a be a set set of all rational numbers p belongs to q such that p square is less than 2. Okay, we denote a by those set of rational numbers whose square is less than 2, and also we denote another set. This set is b, and b is the set of all positive rational numbers. Obviously this one is positive. Okay, so we'll write it q plus, and here all set of positive rational numbers such that q square greater than 2. Okay, then the q square greater than 2. Now we're going to a contains, we're going to one portions. This portions implies that a contains no rational number, and that means a contains no largest number and b contains no smallest. How we going to this portion or this problem? We will also discuss about that, how we going to this problem. Okay, all are understand here. Now going to this portion, how we develop this one. Okay, this one is too easy to handle this one, but we now do it. First so what we done a contains no largest number. We write it a contain no largest number. Okay, and b contain no smallest number. How we do this? We do this simply. For every p belongs to a, we find a rational q such that p less than q. For every p belongs to a, for every p belongs to a, we find a rational number, a rational q in a such that p less than q. Okay, then 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 we going to further. For every p belongs to b, we can find a rational q such that q less than p. Okay. Now we associated for each rational p greater than 0. For each p greater than 0, for p greater than 0, q equal to p minus p square minus 2 by p minus 2 or p plus 2. Okay. Then this one represents p square plus 2p minus p square plus 2 by p plus 2. This implies 2p plus 2 by p plus 2. Okay. Now we're going to some problem. Then what we find? We find q square minus 2 equal to q square minus 2 equal to 2p plus 2 by p plus 2 whole square minus 2 equal to here 4p plus 1 whole square minus 2p plus 2 whole square by p plus 2 whole square. Here we comma, then we 4p square plus 8p plus 4, here 2p square minus 8p minus 4, sorry, minus 8. Okay. Then what we find? We find that this one equal to, we find simply that this one equal to 2p square minus 4 by p plus 2 whole square. Okay. Then if p belongs to a, okay, then what we find? We find p belongs to a means p square less than 2. That means this one equal to 2p square minus 2 by p plus 2 whole square. Then p square less than 2, and this implies that q square, okay, q square equal to how much? P square less than 2. That means q square less than 2. Okay. Then q also, this implies q also belongs to a, but we construct p less than q, then p less than q also q belongs to a. So this implies that p less than q, and all this implies p belongs to a, and p less than q implies q belongs to a. This implies that a has no largest number. Understand? No problem at all. Next we erase this portion. Okay. Then another way we find, we also develop one rational q belongs to b such that q less than p. Okay, and in this way we write this form. Then what we find? We find if p belongs to b. Okay, if p belongs to b, then p square minus 2 greater than 0. Then obviously this shows that q square minus 2 greater than 0. This implies q belongs to b. Okay, that means p belongs to b implies that q belongs to b, and obviously here p greater than q. This implies that b has no smallest number. Okay, understand or any problem? I think all are understand these portions. Okay, so b has no smallest number and a contains no largest number. We prove these portions, and this one important for further progress of analysis. We also give some example, and this one important example. Okay, that means one set who's a bounded set, but this one is not contain his supremum or largest element, and another one is also bounded set and which is not contained his smallest element. Okay, here supremum also exists, but this one is not belongs to this set. Okay, that means not contain this set. So we're going to further progress about that. That means any two any two numbers, rational numbers, then also r is by 2 greater than r less than x if r less than s. Okay, if r less than s, this one hold, and obviously two different number means this one is r greater than s or r less than s. We construct here r less than s, then this one is found, then obviously r plus s by 2 belongs to q. Okay, then we show about that any rational number has, that means any two between two rational numbers, infinitely many rational numbers is exist. Okay, that means this implies between two rational numbers infinitely many rational numbers exist. Okay, and obviously this one hold for any irrational number. Any two irrational number also contains some irrational number. Okay, next we're going to further the definition of something. That means x belongs to some set, that means some element of set. We know about that, but we're going to formal way, so we define this one. Okay, a be any set. Okay, then obviously x belongs to a, means x belongs to a. This implies that x be a member of a. Here we'll give example a 1 2, then 1 2 1 belongs to a. Okay, next also this empty set, that means the set contains no element, then empty set, and this set contains one element, then this one is not empty. That means a set a contain one element. Okay, this implies that a not equal to 5, and empty means no element. Here no element, nothing. Next we're going to subset. We know about that. That means a b are two set, then a subset of b. When a subset of b exists, that means every element of a also belongs to b. Okay, then a subset of a. Next, proper subset of a. Proper subset means this one is subset of a, and proper subset means at least every element of a belongs to a, and at least one element more than a presents in b. Okay, next we're going to further, if one a subset of b and b subset of a, then this implies a equal to b. Two sets are equal. Okay, next we're going to OR set. That means we give some example, also familiar example, and now we're going to OR set. Which set is called OR set? Okay, OR set. Now we're going to part definition of this. S be a set. Let S be a set. Then Then an order on S is a relation. An order on S be a relation denoted by less than with the following two properties. With the following two properties. These properties as first we denoted number 1. If x belongs to S, y belongs to S, then one and only one of the statements is true. That means then x less than y, or x greater than y, or x equal to y holds. Okay. Next we're going to further second one. If x y z belongs to S, then if x less than y and y less than z then x less than z. Okay, understand? Then if these two relations hold in any set, then this relation is called an order. Okay, then this relation is called an order. This one order on an order on this set. Okay. Next, an order set is a set with which an order is defined. That means when we call a order set, an order set is a set which an order is defined. An order is defined. Okay. Next we're going to another problem. That means QBN. We give example QBN order set, because if r less than x is, then s minus r belongs to Q plus. Okay, positive rational numbers. Next we're going to use this problem and going to the definition of bounded above. Then order set we also discuss. Okay, just law of trichotomy hold and also transitivity property hold. Okay, on a relation. Next we're going to another definition of bounded above. So why we use these definitions? Because these definitions are key. Okay, key to handle any problem, or going to further discussion of some problems or some tools of mathematics. Because this we first know about this definition, then we're going to further one. Okay. Next, bounded above, how we handle it. First is be an order set. That means here order set is necessary. Okay, is be an order set and E subset of S. Then if there exists beta belongs to B, S, such that x less than equal to beta, for every x belongs to E, okay, then E is bounded above. Okay, and beta be an upper bound of E. Okay. Next we're going to same lower bound or bounded below. How we represent this one? We represent same thing. SB an order set. Okay, and E subset of S. S be an order set and E subset of S if gamma belongs to S such that if there exists gamma belongs to S such that x greater than equal to gamma for every x belongs to for every x belongs to E. Okay, then E is then this set is bounded below okay, and this gamma be and a lower bound of U. Okay, next we define another definition. Also these definitions are represent supremum. Okay, that means how we handle least upper bound or supremum of any set. Okay, and also give greatest lower bound. Then first we return supremum of some set. How we handle this supremum and mathematically we also see that now. Okay, now we write this definition of supremum first, then supremum of a set. Okay, of a set or least upper bound. Suppose first we construct in this way. Suppose S be an order set. Suppose S be an order set. Okay. Next, E subset of S and E bounded above. And E bounded above. We write also definition of order set and also write definition of bounded above. Then going to further progress. That means suppose there exists an alpha belongs to S and alpha belongs to S with the following properties. First one, alpha be an upper bound of E. Okay. Next, second one, if gamma less than alpha, then gamma be not an upper bound of E. So simple this one. That means then we call alpha, then alpha is called least upper bound of E. Okay, and then we called also alpha be supremum of E. Okay, then we write this definition of supremum also. And now we're going to further discussion about infimum of some set. We write here or not erase this portions. We just write here infimum of a set. Okay. Suppose S be an order set and E subset of S and E be bounded below. Here just bounded below. Okay. And then there exists alpha belongs to S and with the following properties such that alpha be an lower bound of E and gamma greater than alpha, gamma be not a lower bound of E. Okay, then this alpha is called greatest lower bound. Then this alpha is called greatest lower bound of E. Then this alpha is called infimum of E. Okay. Next we do this problem and also give one example. We also read this one. Infimum of a set, suppose S be an or a steady subset of S, E be bounded below. Suppose and alpha belongs to S with the following properties: alpha be an lower bound of E, and if gamma greater than alpha, then gamma be not a lower bound of E, then alpha is called the greatest lower bound of E, and alpha be infimum of E. Okay, now we erase this portion and going to further discussion of some familiar example of sets, and this example have some supremum or infimum. Okay, now we're going to this example where we talk about in first a equal to this p belongs to rational and p square less than 2, and b equal to those q belongs to rational and those q square greater than 2. Then what we find? We find that here a has no largest, that means no greatest lower bound. A has no largest number, that means B has no greatest lower bound in A. Okay, here we see about that. A has no least upper bound in Q. A has no least upper bound in Q, and B has no greatest lower bound in Q. Okay, now we're going to further we discuss about another problem. We're going to give some example. That means we construct E1. Okay, another example. E1 be the set of those rationals R belongs to Q such that R less than 0, and E2 be those rationals R belongs to Q such that R less than equal to 0. Then what we find? We find supremum of E1 equal to 0 and supremum of E2 equal to 0. Okay, but 0 does not belongs to E1, and here 0 belongs to E2. That means one set contains supremum and another set does not contain supremum. Okay, this one important example. We also see another one. Here E, another example. E consists those numbers 1 by n such that n belongs to natural number. Okay, then what we find? We find supremum of E equal to 1, but and also infimum of E equal to 0. Here supremum of E belongs to E since 1 belongs to E, but infimum of E does not belong to E since 0 does not belong to E. Okay, then we stop here. Today we stop here.